In Unit 13, Part 3, we were talking about real numbers. This ties into now after right after sort of some of the examples of irrational numbers as we get to that. So a couple definitions. Real numbers consist of all rational and irrational numbers. So eventually in math we'll talk about imaginary numbers. We're not anywhere near that yet. But real numbers consist of all rational and irrational numbers. Rational numbers are everything that you've worked with in the past. So numbers that can be written as a quotient of two integers. You learned that in 7th grade. But if you look at this diagram over here, the numbers on the left are the rational numbers. So whole numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, etc. Integers, so negatives, -3, -2, -1, 0, and positives, 1, 2, 3, 4. And then rational numbers, which are fractions, or numbers that can be written as a quotient of two integers. And then the third definition are irrational numbers, which are everything that aren't rational. So they can't be written as a quotient of two integers. So the easiest way to tell if something is irrational is if when it's a decimal, it's non-repeating and non-terminating, which we'll talk about in a second. So if you look at this next little table out of your book, it says classifying real numbers. So all three of these, okay, are real numbers. So first we have 5/8, which when you put it in decimal is 0.625. So we say that that decimal is terminating. It ends. Okay, it ends after the 5. So that's a rational number. Our next fraction is 5/6, which is 0.8333333. So we write that as 0.83 repeating, which means its decimal type is repeating. So that's also rational. So if it's terminating or repeating, it's a rational number. Our third example is the square root of 19. If you look, when you do the square root of 19, you get this really long decimal, and the dot, dot, dot means it goes on forever. So it's non-terminating, it doesn't end, and it's non-repeating. You don't have the same thing over and over. So that's what makes it irrational. Okay, so the easiest way to tell for these is when you turn into a decimal. So it says tell whether the number is rational or irrational. So for 2/3, if you divide 2 divided by 3, you get 0.6 repeating. So that's a repeating decimal, which we know that it's then a rational number. For number 2, the square root of 10 is just 10. So that's going to be rational. It's just a whole number. It's an integer. For number 3, the square root of 6 is 2.449489, and it just keeps going and going and going. So that is non-repeating, non-terminating, so it's an irrational number. For number 4, we have the square root of 16 over the square root of 25, which is 4/5. We can make that a decimal, it's just 0.8. So that is a terminating decimal. So we know that it's rational. The next thing we have is comparing real numbers. So just copy and complete the statement using less than, greater than, or equal to. So we're going to want to turn these all into decimals and go from there. So the square root of 7 is 2.64575. And then it goes on forever. 8/3, when you divide that, is 2.6 repeating. So these numbers are the same at the 2, the same at the 6, but then the second one is repeating, so it would be 6 again, which is bigger than this 4. So we would say that the square root of 7 is less than 8/3. We're always going to eat the big one, open to the big one. For number 2, we have negative square root of 2, so that's going to be negative 1.4. And then we have negative 3/2, which is negative 1.5. So again, we want to eat the bigger number. When we're working with negatives, the bigger digits are actually smaller. So negative square root of 2 is greater than negative 3/2. We're eating the bigger one. Okay, number 3, I'll leave for you guys to figure out. On the back side, it says ordering real numbers. It says use a number line to order the numbers from least to greatest. So I don't necessarily need to use a number line. If you don't want to, you can use one if you want. That's totally up to you. But the first thing we need to do is put all of these in the same form. So I'm going to turn them all into decimals. So 2.9 is already decimal. The square root of 10, when I write that as a decimal, is 3.16. 7/3 as a decimal is 2.3 repeating. And 2√2 is 2.8. And some of those, I'm just stopping after a couple of those. So it says use a number line to order the numbers from least to greatest. So if I were to draw my number line, they're all going to be positive, so let's say 0 here. I'm going to have 2.8, and then 2.9, and then 3.16. I actually left out 2.3, so I'd go right there, 2.3 repeating. So now I can put these in order from least to greatest. So 2.3 repeating is the smallest number, so that's 7/3. I need to put it back in its original form. So 7/3 is the smallest, then we have 2.8, which was 2√2. Then we have 2.9, which was always 2.9, and then we have 3.16, which was the square root of 10. So those are now in order from least to greatest. Number 2, I'll leave for you guys. Again, be careful because those are all negatives. It's going to make it a little bit trickier. Then we got a couple of word problems. It says the area of a square is 9/16 square meters. Is the length of one side of the square a rational or irrational number of meters? Explain. So we have a square. Our area is 9/16. We know that area equals side squared. So 9/16 equals side squared. And I want to know if the length of one side is rational or irrational. So I'm going to square root both sides. I'll get S equals the square root of 9/16, which I can split up. And then when I do those square roots, I get 3/4, which I'm going to turn into a decimal to check it, which I know is 0.75. So that is going to be a rational number. That's a terminating decimal. Second word problem says you made a cardboard tree that is 48 inches tall using a stage top for a plate. You need to make a diagonal brace that connected a 28-inch long horizontal brace to the top of the tree. Find the length of the diagonal brace to the nearest tenth of an inch. So I have a tree that is 48 inches tall. So I'm such a great artist. There's my tree. Okay, it's 48 inches tall. Then it says it has, you need to make a diagonal brace that connects a 28-inch long horizontal brace to the top of the tree. So I have a horizontal brace, which is 28 inches, and I need to find the diagonal there. Okay, so we haven't gone over this before. I want you guys to do your best to try to figure that out. If you don't get it, don't worry about it. Then at the bottom are some slope problems that are reviewed. Please make sure you get those done. Let me know if you need help.